Hello and welcome back to Software Engineering. This is CS 470. And today we're going to be going over the second lecture in this textbook, Software Processes. And so this is continuing on in this section that's focusing on this introduction to software engineering. We did a basic introduction, and now we're going to get into a little bit more specifics about what is a software process and what does that look like. And so there's four main things that we'll be dealing with. What are the software process models? What are the process activities that typically take place? How do we cope with change, the change of requirements, the updating the code and whatever? And finally, the discussion on process improvements. So let's talk about a software process. And so a software process is a structured set of activities required to develop a software system. There's many different software processes, but they all involve these four basic things: specification, design and implementation, validation, and evolution. So the first thing you have to do is define what exactly the system is supposed to do. Once you do that, you figure out how you're going to organize it and implement the system with various things. Then after you've done that implementation and design, you need to validate it, check what it does with the customer, see that it meets what the customer wants. And finally, being able to evolve the software to change the system in response to the changing customer needs, or using it and there needs to be something that needs to be modified as you have it in the field over a period of time. So a software process model is an abstract representation of a process. It represents a description of a process from some particular perspective. So in terms of the descriptions, talking about this in more detail, when we describe and discuss processes, we usually talk about the activities. And these processes, such as specifying a data model, designing a user interface, et cetera, and the ordering of these activities, these are things that come up. So process description may also include products, which are the outcomes of a process activity, roles, which reflect the responsibility of the people involved in the process, and the pre and post conditions, where statements that are true before and after process activity have been enacted or a product produced. So what about plan-driven and agile processes? We'll get a chance to get some exposure to these. A plan-driven process or processes where all the process activities are planned in advance and progress and measured against this plan. In agile processes, planning is incremental and is easier to change the process to reflect changing customer requirements. But in practice, most practical processes include elements of both plan-driven and agile processes. So thus, there's no right or wrong answer for coming up with what is the best option for a software process, and consider that. Well, let's talk about software process models. And so we'll be talking about several. First is the waterfall model. So this is a plan-driven perspective model. It separates it has separate and distinct phases of specification and development. Another model is an incremental development. The specification, development, and validations are interleaved, and maybe plan-driven or agile. And we'll be talking about these terms, agile, for example, in more detail. Integration and configuration. And so this would be a system that is assembled from existing configurable components. It may be plan-driven or agile. And so maybe you have existing capabilities or code components that you're trying to integrate together to make a new application. So in practice, most large systems are developed using a process that incorporates elements from all of these models. So here's an example of what a waterfall model would look like. And so the first thing you have is a requirements definition that would be flowing down into the system and software design. Once you have the design and how you see that you're going to go about that, you can do the implementation and having the unit testing of modules. You then integrate that into a larger core, and you have system testing, and finally you do operation and maintenance. And so that gives you an idea of what a waterfall model would look like. And so there are separate identified phases in the waterfall model. There's a requirements analysis and definition. That would be number one. Number two, systems and software design. Number two, you have the implementation and unit test. Number three, four, integration and system tests, and operation and maintenance, as we showed in the figure on the last page. So the main drawback of the waterfall model is the difficulty of accommodating change after the process is underway. In principle, a phase has to be complete before moving on to the next phase. So in terms of the concerns or problems that may be associated with this model is it's the inflexible partitioning of the project into distinct stages makes it difficult to respond to changing customer requirements. That's not exactly how sometimes things are done in the real world in terms of what the customer would see. Therefore, this model is only appropriate when the requirements are well understood and changes will be fairly limited during the design process. And few business systems have stable requirements. So that's something that you probably want to get introduced to now. Things change. A customer may not know exactly what they would want. And the waterfall model is used for large system engineering projects where a system is developed at several sites. In those circumstances, the plan-driven nature of the waterfall model helps coordinate the work. So here's another way of considering how software can be developed. And this is using the incremental development approach. And so first is you have an output description, and then you have these various concurrent activities. You have specification and you iterate back and forth with an initial version. You do some development, and some of that development may be reflecting back into revisions in the specifications. Then you are developing an intermediate version as a result. Finally, in the validation process, that can come back and say that there needs to be some things that are updated in the development. And finally, you get a final version, and then you're done using the incremental developmental approach. So there's benefits for this approach. And so the cost of accommodating changing customer requirements is reduced. You have an iterative process in which you're making this develop. The amount of analysis and documentation that has to be done is much less than is required with the waterfall model. It is easier to get customer feedback on the development work that has been done. Customers can comment on demonstrations of the software and see how much has been implemented. And so you're giving them insight, not just to the final product, but you're giving them insight as the whole software project is developing. You can have more rapid development, delivery, and deployment of useful software to the customer in this kind of approach. So the customers are able to use and gain value from the software earlier than is possible with a waterfall process. So that's the advantage of that. The disadvantage is the process is not visible. So managers need regular deliveries to measure progress. If systems are developed quickly, it is not cost effective to produce documents that reflect every version of the system. So that needs to be considered. System structure tends to degrade as new increments are added. So unless time and money is spent on refactoring to improve the software, regular change tends to corrupt its structure. So incorporating further software changes become increasingly difficult and costly. So that's something to be thinking about in terms of that. But what about integration and configuration? So based on software reuse, where systems are integrated from existing components or application systems, and sometimes this is called COTS, if you've never heard this term, which stands for commercial off the shelf. So you could have COTS systems in various components that you're trying to aggregate together. So reuse elements may be configured to adapt to their behavior and functionality to a user's requirement. So reuse is now the standard approach for building many types of business systems. And so we'll be talking about this in more detail in chapter 15. So aggregating things together from already existing applications or units that have been demonstrated and have been proven. So let's talk a little bit more about types of reusable software. Standalone applications, like we use this term on the last slide, COTS, can be commercial off the shelf that are configured for use in a particular environment. So that would be one thing that we can consider. You can have collection of objects that are developed as a package to be integrated with a component framework such as .NET or J2EE, if you're thinking in terms of an enterprise Java environment. So web services that are developed according to the service standards which are available for remote invocation. So that's another thing that you can have. So standalone applications, you can have objects, collections of objects, you can have web services. These are all examples of the kind of reusable software that you could be having. And so here's a flow diagram of how that can work in terms of having reusable software. So you have your requirements and then you do an evaluation. Do I need to be writing software, or is there already existing packages that I can be using? And so you can go and work through that process, and then you can redefine those requirements, maybe adapted that if you just imagine how you specify the requirements, you may be able to parse things into packages that are already available components. And so then you can, as a result, you can make a decision to say, are there already available system components? And then you just want to be configuring those applications. And if it's not a system, but there's just components, then you need to figure out how are you going to adapt those components, or maybe you're going to have to develop new components. And finally, you're going to have an integrated system that you would be working with. So what are key process stages? There's 5 that we have. There's requirements. You have to define what you're going to do before you can go any further. You have the software discovery and evaluation. What kind of code are you going to write? What is available that you might be able to leverage? And then you do requirements refinement as a result. Then you have the application system configuration, looking at how you're going to do the configuration, and finally component adaptation and integration. So what are the advantages of software reuse and what we've just talked about? So there's reduced cost and risk as less software is developed from scratch. So that's a good thing. There can be faster delivery as you just pull these things together and get the interfaces, the information sharing among those components working properly. But the requirements compromises are inevitable, so systems may not meet real needs of users. And so that's a concern that you're going to have to be careful of. And then there's a loss of control over evolution of reused system elements. So let's talk next about process activities. And so process activities are real software processes that we see that are interleaved sequences of technical, collaborative, and managerial activities with the overall goal of specifying, designing, implementing, and testing a software system. The 4 basic process activities of specification, development, validation, and evolution are organized differently in different developmental processes. For example, in the waterfall model, they are organized in sequence, whereas in the incremental development, they are interleaved. So these are some thoughts in terms of the requirements process. Well, let's look at the requirements engineering process. And so the requirements elicitation analysis, we start with there. And so we have the system descriptions. The system descriptions can then flow into requirements documents. We can have an iterative process of going and coming up with this elicitation of analysis and iterating with specifications to get some clarification there. And then we validate those requirements. Does it actually give us what that would want? And so that would be flowing down into requirements documents. And finally, going through this process of requirement specification analysis, eventually that folds into user and system requirements. And all of those 3 of those things start to have things in the end game of the requirements document that you want to be leveraging. So in terms of a software specification, we have the process of establishing what services are required and the constraints on the system's operation and development. And the requirement engineering process can have several elements. So there's a elicitation analysis, there's a requirement specification, and the requirements validation. So we talked about this on the last chart. The requirement elicitation analysis, this is where we try and figure out what do the system stakeholders require or expect from the system. The requirement specification, this is where we're trying to define the requirements in detail. And finally, the requirements validation is checking the validity of the way that the requirements are articulated. Does it actually work? So in terms of software design and implementation, the process of converting the system specification into an executable system, this is what we're doing in the design and implementation process. So for the design, first the software design, we have to design a software structure that realizes the specification. Then when we have the design, we can do the implementation. We can translate the structure into an executable program. And so I know with this course, and then we get into the capstone project of actually doing the implementation, you first have to be focusing on the design. And so we're going to be focusing more on the design in this class and then move into implementation. The activities of design and implementation are closely related and may be interleaved. So here's a general model of the design process. And so we have to have the design inputs. So the platform information, the requirement specification, the data descriptions, what kind of data do we have? What is it that we want to be doing? What type of platforms are we going to be using? Is it a mobile platform? Is it a desktop application? Is this basically a web-based server-driven type of operation? And then we get into how and what needs to be done in terms of the design. So we have the architectural design, we have the interface design, and the component design, and all those fit into the development and understanding of what exactly how we're going to be designing the database. So then we have the outputs. So we come up with the system architecture, the database specification, the interface specification, and the component specification. So these are the things that we then have figured out as a result of going through this design process. So here are some words that align with what we talked about. We have the architectural design, database design, interface design, and component selection. So the architectural design is where we define the overall structure of the system, the principal components, and the relationships. The database design is where we figure out the system data structures and how these are to be represented in a database, the database schema, and things like that. We then do the interface define as how are the components related to one another and what is the information that they're going to exchange with one another. And finally, having the component selection and design is where you search for reusable components. And if they're unavailable, you have to design for how it would operate. In terms of system implementation, the software is implemented either by developing a program or programs or by configuring an application system. Design and implementation are interleaved activities for most types of software systems. Programming is an individual activity with no standard process. And finally, debugging is an activity of finding program faults and correcting these faults. And so this is what we have. We have the design and implementation, we have the programming, and we have the debugging. So some things for us to be considering as we're going through that process. How do we do the validation? Sometimes this is called V&V, verification and validation. And it is intended to show that a system conforms to its specification and meets the requirements of the system customer. It involves checking and reviewing the processes and system testing. The system testing involves executing the system with test cases that are derived from the specification of the real data to be processed by the system, and testing is the most commonly used verification and validation activity. So here is just a picture of what it would look like in terms of the stages of testing. We do component testing, and then when we aggregate that together, then we do system testing. The components are all put together in their proper relationships. And then we do the acceptance testing. Does it actually work? And so it's an iterative process that sometimes the components testing would be impacting the acceptance testing, and the results from the acceptance testings can be feeding back to things that may need to be updated with the components or the selection of components. So the testing stages, we have component, system, and customer. So the first thing is we test individual components independently. The components may be functions or objects or coherent groups of these entities. And so once you have all of those figured out, you then aggregate that and go to the next level, and then we do the system testing. So this is when something you still do in-house, and you test the system as a whole. And then you want to be looking at the emergent properties. How does it actually characterize, and what does the outputs look like, and does it seem to be meeting what you perceive would be what the customer would want? And then you get into this final step when you actually do the customer testing. This is the customer with the testing with the customer data to check that the system meets the customer's needs. And so we have the testing phases in a plan-driven software and process. And so something that you would see in a V model. And so here we have the requirement specification, the system specification, the system design, detailed design, and that folds into the model and unit code, and test that then aggregates into the subsystem integration and test, system integration test, acceptance tests, and service. And so you can be seeing a V, it's on its side, if you will, that we're going through that. And each one of these going through this process, we have the acceptance test, we have the system integration test plan, the subsystem integration test plan, and we can see how there's a parallel between these different areas as we walk through this flow of this overall process. Software evolution. As you will find, software is inherently flexible and can change as requirements change through changing business circumstances. A software that supports the business must also evolve and change. And although there has been a demarcation between development and evolution or maintenance, this is increasingly irrelevant as fewer and fewer systems are completely new. And so you write what is not there, and then you add on and go forward. So for system evolution, you define system requirements that flows into assess some existing systems, proposing system changes and then modifying systems. And if there are things that need to be modified, then you have a new system. And so we're seeing how these are the ways that things can be evolving, and you can have existing systems that are folding into this process. And so you either have existing systems, you modify systems, and ultimately you come into a new system is what you're trying to focus on. So coping with change. Change is inevitable in large software projects. Business challenges lead to new and changed system requirements. New technologies open up new possibilities for improving implementations, and changing platforms require application changes. Change leads to rework, so the cost of the change includes both rework, that is reanalyzing requirements, as well as the cost of implementing new functionality. If we want to be reducing the cost of rework, change anticipation, where the software process includes activities that can anticipate possible changes before significant reworking is required. So that's always a good thing if you can anticipate change. So for example, a prototype system may be developed to show some key features of the system to the customers, and you may be able to, as a result, figure out that, aha, here's something that needs to be reworked early. And then another area is something called change tolerance, where the process is designed so that changes can be accommodated at relatively low cost. This normally involves some form of incremental development, but proposed changes may be implemented in increments that have not been developed. If this is possible, then only a single increment that is a small part of the system may have to be altered to incorporate the change. So coping with changing requirements, system prototyping, where a version of the system or part of the system is developed quickly to check the customer's requirements and the feasibility of design decisions. This approach supports change anticipation. Incremental delivery is where system increments are delivered to the customer for comment and experimentation. This supports both change avoidance and change tolerance. So prototyping is a really a good thing to consider here, as a prototype is an initial version of a system used to demonstrate concept and try out design options. A prototype can be used in the requirements engineering process to help with requirements elicitation and validation, in design processes to explore options and develop a user interface design, and finally in the testing process to run back-to-back test. So prototyping can be really a great thing to help you to go from one step to the next step. And so definitely something to be thinking about. Benefits of prototyping: there's the improved system usability, a closer match to users' real needs, improved design quality, improved maintainability, and finally reduced development efforts. All of these are wonderful benefits that we have in terms of prototyping. So let's talk about the process of prototype development. So the first thing is we want to establish the prototype objective, and that would result in a prototyping plan. Then move on to define the prototyping functionality, and then we would have the outline definition. This would move on to we develop the prototype and the have an executable prototype, and then finally having evaluate prototype, where we do an evaluation of how well it did. So this just gives you the process and the development and how we can be formalizing that into a structured, useful process. So in terms of the prototype development, it may be based on rapid prototyping languages or tools. It may involve learning, leaving out functionality. Prototypes should focus on areas of the products that are not well understood. So you could have code stubs in certain things. You're just trying to work on these things that you don't have. And so you have the error checking and recovery may not be included in the prototype, and a focus on functionality rather than non-functional requirements such as reliability and security. In terms of throwaway prototypes, prototypes should be discarded after developing, as they are not a good basis for a production system. They're meant to try and help you in this analysis process. And so that's the whole main focus of what you're trying to consider. So it may be possible to tune the system to meet non-functional requirements. Prototyping are normally undocumented. The prototype structure is usually degraded through rapid change, and the prototype probably will not meet normal organizational quality standards. And so it's just a test platform, if you will. In terms of incremental delivery, rather than deliver the system as a single delivery, the development and the delivery is broken down into increments, with each increment delivering part of the required functionality. User requirements are prioritized, and the highest priority requirements are included in early increments. Once the development of an increment is started, the requirements are frozen through requirements for later increments can't continue to evolve. In incremental development and delivery, incremental development, this is the development where you would be developing the system in increments and evaluate each increment before the proceeding to the development of the next increment. Normal process approach is to use an agile methods, and the evaluation is done by user customer proxy. Incremental delivery. So we have incremental development and incremental delivery. So we deploy an increment for the user for use by the end user and have them get a chance to figure out, well, how does this work for them? It's a more realistic evaluation for the practical use of the software. And it's difficult to implement for replacement system, as increments usually have less functionality than the system being replaced. So you might have to have a ghost system that's they can get a chance to have a sneak peek of what that would look like, and they can comment to see if that's something that's of use for them. So in terms of incremental delivery, this is how it would look like. So you define outline requirements, you assign the requirements to increments, then you design the system architecture. Then you start to develop those increments. And so you validate an increment, you integrate the increment into some level of functionality, you validate it, and then you deploy it. And then is it complete? Then you would have your final system. And if not, then you would be developing another increment, and you can be iterating this until you get a complete set of capability that matches what you need for your system. So the advantages is that customer can be delivered, the customer value can be delivered with each increment. So system functionality is available earlier. Each increment acts as a prototype to help elicit requirements for later increments, and it lowers the risk of overall project failure. The highest priority system services tend to receive the most testing. In terms of incremental delivery problems, most systems require a set of basic facilities that are used by different parts of the system. As requirements are not defined in detail until an increment is to be implemented, it can be hard to identify common facilities that are needed by all increments. The essence of iterative processes is that the specification is developed in conjunction with the software. However, this conflicts with the procurement model of many organizations where the complete system specification is part of the system development contract. So now let's talk about the process improvement as the next part of this lecture. And so for process improvement, many software companies have turned to software process improvements as a way of enhancing the quality of their software, reducing costs, or accelerating their development processes. Process improvements means understanding existing procedures and changing these processes to increase product quality and or to reduce costs and development. So the approach to improvement, the process maturity approach, which focuses on improving processes and project management and inducing good software engineering practice, the level of process maturity reflects the extent to which good technical and management practices has been adopted in organizational software development processes. The agile approach, which focuses on the iterative development and the reduction overall heads, is the software process. The primary characteristic of agile methods are rapid development of functionality and responsiveness to changing customer requirements. So this is how we have these things. And so we have these things all together. So you measure, analyze, and change, and you just iterate through that as you go along. So in terms of process improvement activities, there's a process measurement. You measure one or more attributes of the software, process, or product. These measurements form a baseline that helps you decide if process improvements have been effective. That's number one. Process analysis occurs. The current process is assessed, and the process weaknesses and bottlenecks are identified. Process models, sometimes called process maps, then describe the process, how it may be developed, and finally process change. These are the changes are proposed to address some of the identified process weaknesses. These are introduced, and the cycle resumes to collect data about the effectiveness of the changes. So in terms of metrics, time taken for process activities to be completed. So that's something that we can be using as a metric. You can use the resources required for processes or activities and the number of occurrences of a particular event. And so in terms of the capability maturity levels, we can have the level 1 for initial, going up to manage, defined, qualitatively manage, and finally optimizing. And so those are 5 levels of optimization. And so here's some more words. The SCI Capability Maturity Model, or the Software Engineering Institute. And we saw that as listed on the last chart. And so it goes from it's going from relatively uncontrolled. You have the product management procedure defined and used, and it's repeatable in terms of the defined, the process management procedures and strategies are defined and used. The managed is a quality management strategies defined and used, and the optimizing the process improvement defines and used. So finishing up here, the key points: software processes are the activities involved in producing a software system. Software process models are abstract representation of these processes. General process models describe the organization of software processes. Example of these general models include the waterfall model, the incremental development, and the reuse orientation development. We showed examples of what that looks like. Requirement engineering is a process of developing a software specification. Design and implementation processes are concerned with transforming a requirement specification into an executable software system. Software validation is a process of checking that system, that it conforms to its specification and that it meets the real needs of the users of the system. Software evolution takes place when you change existing software systems to meet new requirements. The software must evolve to remain useful. And finally, the process should include activities such as prototyping and incremental development to cope with change. And then for our last chart on key points, processes may be structured for iterative development and delivery so that the changes may be made without disrupting the system as a whole. The principal approach to process improvements are agile approaches geared to reducing process overhead, and maturity-based approaches based on the better process management and the use of good software engineering. In the SEI process maturity framework, identifies maturity levels that essentially correspond to the use of good software engineering practices. So thank you very much. And that's it for this lecture.